Hello again. So this is the third video. The last time we left off at the stage that we were gonna talk about the particle advection. So why are we creating a particle advection when we already have a nice simulation that we did here? I think it was frame 40. So if we look at the nebula images on the internet, you're gonna see a lot of concentrate. Here's the one I found on the internet. I don't know if it's real. I think it is. So, like, if you look at these sections, there's a lot of concentrated, denser areas. It's almost like this guy, or all this stuff here. You know, it just looks like an advected particle. And we do need to figure out a way to create these additional details. Although we don't need like all the nice edge breakups and everything, because that's going to come from the procedural shader, but we do need a place to tell the renderer, here is my dense area. So obviously a good option for this is particle advection. So let's start by preparing our setup. So we had our particle cache, the volume cache here, 40 frames, that's good. And right underneath, I'm going to I put a time shift. So I said, okay, you know what, just freeze it at frame 5. So you will have the expression here by default, right? Excuse me. And then you need to right click on the frame and then delete channels. Set your frame number. So it's gonna always, from this branch down, it's gonna always stay at the 5th frame of the cache. So then I'm just scattering points at the stage using the scatter tool. Eventually I went excuse me again. Eventually I went down with 2 million points. And I just create rest points on these particles points in case I want to do something with them, just in case. So now what I'm gonna do is I'm gonna remove a digit for the sake of speed here. Even another one, I guess. Okay, and I'm gonna dive inside the particle.network. So here you can just tab and then go pop network. That's gonna create one default for you already. So let's dive inside. Very simplistic. Just rename this pop object to stars. So the only added thing is this guy, because by default it's all these 1, 2, 3, 4 nodes. So let's select the pop source. I set it to all points like I did before, because I wanted to drive the amount from outside. And impulse activation is set to $F less than 2, so it's going to emit for 2 frames. And then in the pop advec volumes, I said from the second context geometry, fetch velocities, and settings are velocity scales at 1. And the settings I played, I thought velocity was the one that was working the best. So then first input of this network is our particles. Second input of our .NET is our pyrosim. And the only thing that we really need for this to work is this velocity fields. So if I dive inside and just press play. So now the advection is in progress. And if I get closer, I'll start seeing denser areas as opposed to sparse areas, and I'm interested in these denser areas. So after your particle.network, what happens is, this is by default, it's good practice. By default, we get like these 10 attributes and the detail attributes and everything. So it's better to just put a group delete here. So I'm just going to delete all the groups that used to be here, just optimization for optimization's sake. And right underneath, put an attribute delete. So I just deleted what I'm interested. Actually, I don't even need that. Or in the, actually, I can do this probably. At velocity, at rest. Okay, what else do I need? I may need, well, they're all same age, so I don't really need age actually. So anyway, and then because we have 40 frames of pyro simulation, so I cached out 40 frames of advection. So let's load this. It's going to be a little heavy, I think. Yeah, so if I go to frame 40, let it load. points, but if I get close, now we really have some kind of structure in there. It's not just uniformly distributed points. So if I look like this, and we do have a lot of filaments. So now we need to isolate those filaments a little bit better. So what I'm going to do now is put a timesheet, because our nebula is static, so it's at frame 40, and put a point warp. So this is going to give me a density map, which we're going to dive inside. And I guess this was taking a little bit time, because so basically this point warp is calculating the sparse areas as opposed to dense areas. As soon as I dive inside, I will be able to show that to you. So let's let it cook a little bit more. Okay, it's done. So it's creating this density map for me. So what I'm doing here is quite simple. So we drop a point warp. So let's name this actually density mapper. Okay, whatever. And I just changed the name, so it's going to recalculate now. Bummer. Okay, just need to wait a little bit more. While this is cooking, we can talk about something. So a lot of times that I try to make an image like this, I really struggled, and I think it's the creating a nebula-like structure is very difficult. But then I realized that some of the magic lies in the contrast it has within itself. So it's like you have this almost like black particles, right? And then you have this light source, and so there's like everything in here. It's not just a gray smoke, right? It's not just a gray smoke that is lit by some stars as well. It has its own properties. It has its own color as well. Like the gas, it has its own color, I suppose. So if we go back in here, we're going to use this field to achieve exactly that. And I think maybe I should put this on. Maybe I should just remove some of the points just so we work a little faster. So let's just wait until this is cooked. Okay, so in this attribute warp, the point warp, we're going to drop in a PC find radius. So basically this is going to search against itself per point to find if there is a point in certain distance, and if there's at least 40 of them. Okay, so these are the values that worked, the distance and the points for my simulation. You will need to obviously play with it to see what the result is. So actually I think I can put a color support, actually visualizer here, so we can see what it looks like. And we're going to go to visualizers, change the density, ramped attribute. I'm just going to plug this guy here. It's going to take a little time to draw. Okay, so our density is visualized here. So the red areas are most dense sections, and the blue ones are quite sparse. So what we are interested in isolating the dense areas. So if I make that bigger, this computer is not the best. It's a good gaming machine though. It's an Asus ROG Strix. It's alright. Has a 1650 GeForce video card and 16 gig RAM. So I'm right now. So what you saw is that is made on a 16 gigabyte RAM machine, which I guess should answer some of the questions I see a lot of time on the internet. Like, do I need a 128 gig RAM? Do I need a 64 gigabyte RAM? No, guys, you don't need such huge amount of RAM to output amazing quality simulations or looking effects. It's just that we need to really optimize our workflow, and the fewer amount of memory it requires, better it will render, faster it will render, it will, and then you can add more if you have the memory, of course. just to make it a bit more interesting. So let's dive back inside here. So what this PC find returns is that per point, it returns an attribute, which I'm not exporting here. It's an array. So it says like, maybe this one has 50, this one has 10. And then I have, if you tab and type len, the array length is going to return a value that it's going to basically return the length of the array, which means that I have 10 members, so my value is 10, whatever. And so I put a fit here to fit this value, and then my source max is linked to how many points I want max. So I'm remapping it from 0 to 40 to 0 to 1 and exporting it as a density attribute, which you can create by saying by an export, and then you type density. Now I dropped it, so it's going to recalculate. I'm just going to kill it actually. Okay, need to be more careful so you guys don't wait. Come on. Okay, so while it's cooking, let's go back to this topic. Other nebulas here, it's like there's a lot of contrast everywhere. Of course, most of these are artist renditions, or a lot of post processing is done. This one is particularly very, very nice. And has a lot of detail. It's these things are amazing. All right, let's go back. I think it's done now. No, it's still not done. It's a bit annoying. Maybe I can pause the video and then come back, but I'm not sure if this pausing is gonna work. Okay, you know what? Let's just put this on manual for now. All right, so I have a lot of points. So I made two attribute wrangles right under this to define some stars. So in this left branch, I just dropped in an attribute wrangle, and I say if the density is bigger than whatever value is where I'm going to fetch some of these stars that you can see in the render, which I will play here. Let me go back to my project settings, and I guess I can probably play this one. So yeah, so from the initial spread out simulation, I picked the sparse ones, so I kind of like remove the dense areas, and then I'll go a lot less percentage of this to do the rendering. So this was my star field. Okay, let's go back in here, and then I go just put a delete swap, and I say like, okay, just get, I think it's like 0.9% of the points. So how many stars I have here? Only 3,500 almost. All right, so this is what I render, and then I excuse me, and then because they're not moving or anything, I just removed every attribute, 363 kilobytes, just to save some space. On the middle branch, I have another attribute wrangle, but this time I'm doing the opposite. I'm removing the sparse points to keep the dense areas. So if you look at the output, so these are now my filaments that we are going to still convert to volumes. We don't render the particles. We'll render them as volumes, and then we're going to displace them with the vex volume, and then we're going to give them a color that is dark to create our contrast regions, which we can see in certain areas here. So, and actually this was the only time I actually could finally see a result, like adding a lot of tiny amount of detail to this volume. So again, I do my cleanup here, and then I save it out as a single file. So it's called, this one is called filaments, this one is called stars. So then the next step is to convert this to a volume. Therefore, I guess this is probably not needed here, it's obvious. So then I'm going to drop a VDB from particles. So what I do here is it's important not to have a p-scale coming from the .NET, because then you will have to fight with the settings to make it work. So we are going to right click on the voxel size and then connect it to the point radius size. And then I don't have any conditions based on minimum radius. I'm just going to drop this to 0, which is the settings here. So let it cook a little bit. And that's it. Okay, so now we have our filament layer that we want to use. So that's one branch. Now let's go back up, straight from PyroSim. We are loading again the same frame, so with a time shift, drop it, and then break the expression at 40, and then let's load this guy here. So this is my softer volume, that is the outer shell, and we're going to go inside and drop in a convert to VDB node. So it's a VDB now. It's no more a regular volume because we use VDB operators, so we need to convert them. So what I do now is that I have 3 separate branches here. On the left side, I am only keeping the temperature. I'll bring it down here, but this is because I'm going to process some of this data here. Because remember we had the, so I guess we can show that here too. So I still want to have the access to my temperature field to use it as a geolite. So if I go VDB volume visualization, drop this guy here and say density, make it dense, I guess. Okay, and then if I go temperature here, still use the same. I guess change it to black body. If I start pushing this guy out, you should start seeing some heat building up. Okay, so I still want to be able to use these guys as I think let's go 50. Okay, maybe we need to bring this guy down a little bit to crunch the values. No, let's go on. Let's try the emission field. Okay, so it's still interesting, and I still want to use this temperature field as a volume light to light my volume as well as its own self. So that's why I isolated this here. So this is only my temperature field, and if I want to do anything specific to it, I can do this under here. And then in here I have my density. I isolate my density. Now what I did is that I dropped, so basically you just type, you can do a drag down, and then you can select any field you want to isolate and then delete not selected, and it's going to remove everything else. So instead of all this stuff here, is all here. I mean, we can generally just do this under one branch using the groups, but visualization wise this is a lot easier to work with, I think. So what does the VDB activate do is that it's expanding our VDB3 further out. So what I'm doing here is I put in VDB activate under my density node, and then I go voxels to expand. So I expanded 10 voxels. So if I want to visualize, what it does is that I can put a visualization tree here. I believe that should work. And then if I put it here, so you get like a little expansion. So if I want to create, it's basically because VDBs are optimized, so I'm basically creating an extra layer in case I want to push things and create new volumes. So now at this stage I have a density that's slightly bigger, fine. And then on my third branch I keep my velocities, and then I'm converting my velocities to a single velocity field using VDB merge. So it becomes like, instead of XYZ, it becomes well. And then the next thing I'm doing is now because I need a color field, and it needs to be a vector because color is a vector. So I'm just gonna rename. I don't care about the values. I'm just renaming it because I'm gonna overwrite them inside my shader anyway. So I just need the field though to be actively there. So I just use a name swap to change whatever is coming to color instead of velocity. So now on our left end we have our filaments, we have our temperature field, we have our density, we have our color, and then we have our velocity. So now I'm going to merge all of these guys into one node. So then I have my density, temperature, velocity, filament, color. That all the cool stuff that we can do. So then I save this out as volume fields. So let's load the layer. And from here it starts getting more interesting. Okay, so pretty much now we are ready to dive into our CVX volume displacement shader, which we're going to explain what this does and how it does it. Okay, so I'm going to pause the video and then we will move on to the shader in the next one. Thank you for watching.